Birds are very agile, way more agile than our aircraft. But some birds are more agile than others. In this podcast, we're looking at why that is. And to do that, we're looking at this research called Birds Can Transition Between Stable and Unstable States via Wing Morphing. It's open access and you can find it in the link below, and the DOI is just under the page on the left here. So a bird's flight is pretty complex. It can move in 3 different directions in straight lines, so forwards and backwards, left and right, and up and down. On top of that, it can then move in 3 rotational directions as well. And these are a little harder to imagine, so in figure 1 in the top left part of 1A here, we see a coordinate system. So to explain them, imagine you're behind a bird and looking forwards. So the bird can yaw, which means that it can rotate from left to right. It can also roll, which means that it tilts one side up and one side down. So for example, the left side tilts up while the right side tilts down, or vice versa. Then we have pitch, and that is when the head tilts up or down more. For these 3 straight or translational directions, the mass of the bird is important because that heavily affects how fast it can move. For the rotational directions, then we actually care about something more called the second moment of inertia. It's a weird term, and the equation for it is given on the top right of figure 1A here in this little matrix with these different integrals. You see these I terms with this integral around it. Effectively, what is happening here to calculate it is you're summing the mass around the object to find out how much there is and at what distance away from the center each one of those bits of mass is. Each of these 3 directions has a second moment of inertia, so x, y, z, and then the cross as well. And the higher the number is, the harder it is to turn in that direction. So for example, let's say you have a long stick, if you know what I mean. To twist it about its length, it's very easy. But if you wanted to twist it end over end, then that is much harder, and you need to use more force to do so. That's because if you spin it around its length, the second moment of inertia in that direction is very small. Twisting it end over end, though, means that you have a much greater second moment of inertia to overcome. And the exact same thing applies to birds. The lower their inertias are, the faster they can turn and accelerate. So that is one way to quantify how agile a bird is, and how low these values are really determine that. But from a flying point of view, there's also another way, and that is to use a stability approach. So this is quite complicated, but in my opinion, the hardest thing to get right when flying is stability. Getting in the air is not that hard, it's more staying in the air that's the difficult part. So in figures 1A and B, in the top left here, among them we see a bunch of symbols including a black square that is termed NP, then next to it another circle called CG. NP stands for neutral point and CG stands for center of gravity. Now the authors do a pretty good job going through and explaining how these 2 things affect a bird's stability and what they are. So if they say here that if the neutral point is behind the center of gravity, then the bird will be statically stable. What that means is that if the bird pitches upwards, so the head tilts upwards and the tail goes down, it will naturally want to tilt back down again so it's neutral, so back where it was. And why is that though? Well, that's because at the neutral point, we can say that the lift produced along the entire bird acts through that point. The center of gravity is where the mass of the object acts through as well, and perhaps more importantly, it's the point at which the bird will rotate around. So because the neutral point is behind the center of gravity, the lift produced by the bird will rotate the bird downwards. On the other hand, if the neutral point were in front of the center of gravity, this bird would be said to be statically unstable. That's because the lift produced would force the bird to rotate upwards. But now we have one question left. So what? Why does it matter if the lift makes the bird rotate up or down? Why would that make it less or more stable? Well, it has to do with how lift is produced. So lift is produced here, either by a bird or by a plane's wing, by creating lower pressure on top of the wing and then higher pressure underneath the wing. That creates a pressure difference and hence a force is created. That force is upwards and that is lift. Historically, the greater the angle of attack of the wing is, the more lift it will produce up until a certain point. After that, the flow will separate over the top and the wing will stall. Lift will then suddenly drop. Now, birds don't necessarily have this exact problem because they can articulate their wings and they also flap. So there's a little bit of a different way of producing lift going on here, but still the same general idea applies here. So the reason why having the neutral point ahead of the CG is bad is because if you have that, as lift is produced, the bird rotates upwards more, and you get pushed closer to the stall angle of attack. But in addition to that, The lift also increases as you increase the angle of attack more as well. So as you tilt it up even more, this vicious cycle just continues. And the bird wants to eventually rotate up so much that it will stall and fall out of the sky unless it recovers in time, but even still, it's very difficult and unstable. So that is what static stability means in the longitudinal direction, so in this forwards-backwards direction. And just to clarify it completely, if the neutral point is behind the CG, then the bird will naturally rotate forwards more. That lowers angle of attack, so the lift produced is less, and there will be a point where no lift is produced at all, and the bird won't want to rotate forwards anymore. That makes the bird stable because it's not getting to the stall angle of attack. It wants to rotate down away from that. So all this explanation is important because it's a way of determining how stable a bird is. And for flying, stability and agility are actually two different and opposite things. That's because if you want the bird to be stable, that means it doesn't want to change from what it's already doing. But agility is the exact opposite thing. If you want it to be agile, you want it to change quickly. So the more stable a bird is, generally the less agile it will be too. So to determine how agility affects birds' flight and how certain birds are in terms of agility, the authors measured their stabilities. If you'd like to learn OpenFOAM, which is a very powerful CFD software, then check out our Black Friday specials here on our courses. Now in figure 1G here, the authors plot how much each bird can flex its wrist and elbow. So to understand what that means, the wrist and elbow of a bird, in figure 1D, we see the bird in blue here, that is the elbow, and that's how the wing can rotate based on how the elbow is flexed, with these little blue arrows. The red writing is for the wrist and how the wing can flex based on its rotation. So figure 1G here, we see that not all birds are created equally. Some can flex their wrists and elbows more than others. For example, the western grebe in the top row, second from the right here, it can flex both its wrist and elbow a lot. So it has a huge range of motion for its wing with these two joints. On the other hand, the sharp-skinned hawk, which is in the second row and the rightmost figure, it can't rotate its wing from the wrist and elbow very much at all. It's one of the least flexible in that range. Now, the amount the bird can rotate its wing might have an effect on its stability because perhaps it could change the center of gravity because you're changing how the wing is located. So pulling it back more means that the weight is being pulled backwards more, so the center of gravity would probably move backwards too. Because we know that the relationship between the center of gravity and the neutral point is heavily indicative of the stability of the bird, if the center of gravity position changes, then that will also change the stability as well. So in figure 2, we see how much the CG changes with all these different changes with the wrist. So in figure 2a, we see the birds, and about when they first appear in evolution, and this is actually quite important, we'll see this later, how this comes into play and the effects it has on their performance. It's quite interesting how through evolution, a bird, how it moves, has changed quite a lot, and we have a very different way now compared to a few hundred million years ago. Anyway, the second column, so figure 2b, we see how much the center of gravity in the x direction, so along the bird, from the tail to the head, and the direction that determines the pitching stability, how much it changes when the wrist and elbows are rotated through their ranges of motion for each bird, as found in figure 1G. Now in addition to that, we also see how much the CG changes with shoulder rotation too. So that's in figure 2C. Sorry, 2B as well. We'll cover that in a second. So the shaded box is the amount it changes based on the rotation of the shoulder, while the dots show the extreme ends of the center of gravity position based on the elbow and wrist position, So the surprising thing is that for most birds, the elbow and wrist rotations make almost no difference to the CG. At most, there is like a 10% change, but most are around 1 to 2%. So what that means is that the wrist and elbow positions don't affect the CG, and if the neutral point isn't affected either, then the static stability isn't really affected here either. So the wrist and elbow positions aren't affecting the stability it seems, and that's quite surprising. That means that these birds, and probably birds in general, don't use their wrist and elbow flexors to change the stability. On the other hand, the shoulder rotation has a very large effect here for some birds, up to 20% change. So you can see this shaded box here, and the little legend down here, it spans almost 20% for some of these birds, like the barn owl. So for the CG to move 20% is huge, and could easily change the bird from being statically stable to statically unstable, And it's actually really good because that means that the bird has a choice to be stable when it wants to be, like during cruise. But then when they want to be agile, they can rotate their shoulders and change their agility and their CG and become statically unstable perhaps. So the shoulder rotation is far more important here for the CG position than the elbows and wrists. Hence, some birds are more agile in that sense. Now, if we link it back to the left column, which shows when each species came about, it seems like the general trend is that newer bird species don't have this shoulder rotation, so this shoulder rotation CG relationship nearly as much. The older the bird species are, they have far more change in the CG location based on the shoulder rotation. As such, it means that this method of using shoulder rotation to change the CG location and possibly the stability and the agility of the bird too is an older method that isn't used as much by evolution anymore, and that's pretty cool. So why do some birds have greater changes in their CG based on their shoulders? Well, in figure 2D on the right here, we see a potential answer. So the graph, the x-axis here, has the ratio of the maximum wingspan of the bird relative to the body length. So the greater this value is, the greater the wingspan is compared to the body length itself. So it's just like a really flat, long, stretched out bird. On the y-axis, we have how much the CG changes because of the shoulder. So there's a clear relationship here where the greater the wingspan is compared to the bird's body length, the greater the CG movement is too. That makes sense because the greater the wingspan is, the longer the wings are, so moving them will change the CG more too. And what that really suggests is that evolution has kind of favored smaller birds so far, ones with shorter wingspans, relatively speaking. If you want to see how aerodynamic your car is, we can simulate it for you, let us know here. Anyway, let's now move on to figure 3 because there is a bunch of different things to see. The things I'm interested in most is all this data on the bottom row here. So the leftmost graph shows how the second moments of inertia differ between the 3 directions for different birds. So remember that the second moment of inertia tells us how easy it is for a bird to rotate about that axis. A small value means it can rotate much easier. Now, the thing to look out for here is how similar the values are between the directions. So for example, let's take the first bird, the mallard, which is a duck if I'm not mistaken. Here, 2 directions have about the same moments of inertia, about the same, so these circles and triangles. What that means is that it is much easier for the bird to rotate in those 2 directions that have smaller second moments of inertia than that larger one. Now, if we look at the general trend that stands out here, effectively the larger the bird is, like a pelican, the greater the second moment of inertia is in the forwards direction, so this square here. In other words, smaller birds are more agile because they can turn in all directions more equally. Larger birds can't roll as easily and even yaw either as easily. So what that means is that they are better at general cruising where they don't really turn very fast, they just do it gently and either through rolling or yawing. But generally the smaller birds are more agile than the larger birds. But this graph has even more information than that. So for example, in figures 3, D, E, and F, we see how each of the bird's different parts of their body contribute to the different moments of inertia. So the graphs show these colors that make up the total inertia. The key for these colors are above in the top right section here. So the dark gray is for the tail, the medium gray is for the torso, the light gray is for the neck, the light green is for the head, and so on. So for figure 3D, we see the inertia moments in the forward axis, in the x-axis, and as shown in the top right picture too. So for this graph, we see that the bones of the bird make up a decent amount of the second moment of inertia in this direction. But for almost all birds, the feathers make up the largest percentage of this inertia. What that means is that the feathers are increasing this moment of inertia the most. For the tail, torso, and head, they make up almost nothing, which is because while they might have weight to them, they all lie on the forwards-backwards axis along the bird from front to back. So the mass they do have isn't far away from the axis, and so the second moment of inertia doesn't really increase by them very much. They don't contribute to the second moment of inertia here very much at all. The feathers, because they are mostly on the wing sections and are located far away from the axis, they increase the second moment of inertia a lot. So in terms of performance, what that means is that to reduce the moment of inertia here and make it easier for the bird to roll left or right, the feather weight or location of them should change. That will yield the greatest drops in it and make the bird more agile in that way. Now for figure 3e, we see the contribution of these parts of the bird to the y moment of inertia, so the axis that runs left to right, and that is for pitching for the bird. So for this axis, the bird's head, neck, and torso and tail have by far the greatest effect on it. So these sections are what make it harder for the bird to pitch. That is because these sections lie the furthest away from the y-axis, which is the direction that the bird tilts downwards or upwards to increase angle of attack or decrease that. And for figure 3f, we see how these different bits of the bird make up the second moment of inertia in the z direction, so for the yaw. Here there's a very special and large spread in the results, it's quite varied. For example, the Lady Amherst pheasant, so the fourth from the topmost, most of its second moment of inertia is in the z direction, so yaw is made up by the tail, so there's a very dark grey region. That's the tail that's making up most of the second moment of inertia here. On the other hand, if you look at the American white pelican, which is about in the middle of the range, none of its second moment of inertia in the z direction is made up from this tail. So each bird varies quite a lot, and each section of the bird makes up a different amount in this direction. So overall, it seems like smaller birds have less of their moment of inertia made up by their tails and even their heads and necks here. Larger birds have more of their inertia made up by these sections here. So that is a major difference in the physiology and the resulting flying characteristics based on the bird's geometry. So that data alone indicates why some birds are more agile than others. Some have more rounded distributions in the second moment of inertias in all three axes, which makes them more agile overall. Other birds, particularly large birds, are much more stable in certain directions more than others, and usually in the directions that make them more stable in cruise. But now in figure 4, we see something called the pitch agility and the static margin in the top left here. So the pitch agility is what it sounds like. The static margin is a little bit of a different thing though. So the static margin tells us how far behind the neutral point the center of gravity is, or vice versa. So the further back the neutral point is from the center of gravity, the more stable the bird will be in pitching rotation. But sometimes it can become too stable where you try to change the angle of attack too much, but it doesn't do much at all. So the static margin is too great now. So for both of these top graphs, the x-axis is the body mass, while the y-axes are for the pitching agility and the static margin respectively. For the left graph, there is a clear relationship between the mass of the bird and how agile it is. The lighter birds are definitely more agile. What's more, these birds can change how stable they are. They can also go from being highly agile and stable to highly agile and unstable. If the heavier birds don't really have as much of that option. What's more, for the right graph, which shows the static margin, the larger birds can change the static margin over a much greater range than the larger birds. So the lighter birds, not the larger ones. So the smaller birds can change the static margin much greater than the larger birds. And one thing to note here is that for all the birds, while they could mostly change from stable to unstable, they are definitely skewed towards the stable side more, and that makes sense. I mean, it's easier to fly when you're stable. And while that might be the end of this paper, it's actually not, because later on, we see some more sneaky graphs, and the one that I'm very interested in is actually the extended data figure 1. And if you want to look at these figures more, you can download this paper as well anyway. But in this graph here, this shows how the elbow and wrist angles of each bird affects the static margin. The thing that interests me the most is that there's kind of this general trend where as the wrist is angled less, the static margin increases. So the bird becomes more stable. But there are some cases where that trend isn't true. For example, for the Canada goose, which is the top row second from the left, there's a sweet spot where reducing the wrist angle even more reduces the static margin. The same as for the regular pigeon as well, which is on the top row and around the middle of the region here. For the elbow angle, there is also a strong trend where reducing it increases the static margin. So it's pretty clear from these graphs that the physiology of the birds and the way their wings move are responsible for why some birds are more agile than others. And then there's also another factor that the bird's mass also affects how agile it can be, but then it also seems like evolution also played a major role where newer birds don't flex their wings in the same way as older birds for the same purposes. So there are a bunch of different reasons why birds might be more agile than others. And with that, we come to this podcast. If you liked it, hit the me liking and subscribe buttons. And if you want us to simulate your very own car, let us know in the link below. And if you want to learn OpenFOAM, then check out our Black Friday sales below. And if you want to learn more about bird aerodynamics, then check out this video on our channel. Peace out, amigos.